All right, so in this video, I want to look at question number 5, which is right here. Kind of highlighted in yellow, so maybe it's a little easier to see. Oops. Easier for me, at least. All right. It says a crate which has a mass of 45 kilograms is being pulled up a frictionless inclined plane, which meets the horizontal at an angle alpha equals 35 degrees relative to the horizontal by a slope as shown to the right. All right. And the first thing they tell us in part A is to complete the free body diagram showing all the forces acting in the crate as it moves up the incline at a constant speed. So even though it's moving up the incline at a constant speed, when we look at the diagram right here, we can't readily see it, right? I mean, you can't see the movement. Let's go, and maybe you might say, well, I can see that arrow right there on the end of the rope, but you can't, you don't know it's a constant velocity from the picture, right? You have to be told that. So let's go ahead and draw that down here. I'm just going to draw the same picture right here. And this is question number 5. Let's see, okay, these are a dotted line here. Not that it really matters, but I'm trying to keep it the same. This is the angle alpha. We have this mass attached to a rope, and I think they tell us, I'll just write the letter M, that the mass is 45 kilograms. And the velocity is constant. So I'm just going to make a little note here that there's some V here and that it is a constant value. All right, good. So the first thing we do is draw a free body diagram. We have 3 forces here. We'll start by drawing a dot in the center and labeling some of these forces. I think they tell us no friction, right? And that's why I just say 3. Yeah, frictionless inclined plane. All right, so the first force we'll go ahead and label as gravity. Should be the most obvious one. So we'll call that Fg. And I'm going to write it over here to the left on purpose. So make sure you do the same. The second force is force normal, which always points 90 degrees to the surface. So 90 degrees is perpendicular to the surface. And so we're thinking something like this right here. I'm going to use lowercase n. All right. And then we also have a force from this rope, a pulling force, which I'm actually going to call tension. I could just call it force pull, but I'm going to call it tension since it's coming from a rope. Unless they call it, let me check real quick to see what they might already call it force pull. No, they don't tell us anything about it. They just say it's being pulled. And okay. Yeah, okay, so they do ask in question C, what will be the magnitude of the tension in the rope? So I'm gonna, like I said, just call this tension. That's pretty much the norm. Anytime you get a pulling force from a rope, you just call it tension, which is represented by the symbol big T. Okay, so there are 3 forces, and we're good. We're ready to start. So this is that is part A. This is our free body diagram. And when we do these problems, right, we know that we have to use a tilted axis. We've talked about this before, where we take the axis that is normally, up is positive y, down is negative y, and right is positive x, left is negative x, and we tilt it so it looks like this instead. That this is the new y direction, positive y, and this is the new negative y, and this is the new positive x, and this is the new negative x. Now the reason we do this is because we have a force that doesn't agree with the normal. We have 2 forces actually that don't agree with the normal way of doing things, right? Fn and T. So rather than split those into their parts, their components, it's easier for us to use this use them, have them be the normal now, the new normal, have them point in the positive y and positive x, and then just work with FG. So now FG is going to require components that agree with our new axis system. So if we look at that, we can see that FG, a piece of FG, is going to point and oppose force normal. And we'll call this FGY. And a piece of FG wants to cause the crate to slide down the incline. And we'll call that FGX. And when we do this, we create a 90-degree right triangle right here with 90 degrees. And therefore, our hypotenuse is force gravity. And this angle, because of the way the geometry works, this angle alpha, which is hanging out on the bottom left corner, right, this angle, it's actually going to end up in our triangle, which, and maybe this is hard to see the triangle, so let me highlight in orange, right? This is my hypotenuse. This is a piece of my triangle. This is another side to the triangle. And so this orange triangle that I've highlighted has that yellow angle in it. It just so happens that it's right here, that is alpha. So let's go ahead and color that in with yellow. All right. And the reason we need to know that is because that gives us some direction, right? That FG of X is an opposite because it's across from the yellow angle. And FG of Y is next to the yellow angle alpha. So this is going to be an adjacent. All right. So that is what we have. Now, when we look at this, you can actually do one more step. I like to call this the redraw step. And what it does is it kind of gets away from the idea of the free body diagram a little bit. And it just kind of makes us realize what's going on. So it's just an understanding step. So this is an optional step. You don't have to do this, but it helps with understanding. So here is what is happening, right? We have this mass being pulled by a rope. I'll just redraw my forces, my components, right? So these components are acting here. And by redrawing them right here, I'm not going to redraw FG because I'm replacing FG with its components. So that's one point of doing the redraw step. Another point of it is that you noticed FGX, I moved it, right? It was just kind of hanging out on the bottom of this triangle. I picked it up and moved it up to where it was acting, right? Which is right here at the object. And so sometimes students forget that FG of X is there because it's just kind of hanging out at the bottom of that triangle, just kind of floating around in the middle of nowhere. And it's actually acting right there. And so that's a good reason to do the redraw step. So it's helping make sense of this. This should all make sense, when we're working through these problems. So this is really what's happening right here. These four forces or components are all acting on the mass like this. But when I'm solving it, it's going to look like this, which is kind of confusing. So this redraw step is just to make things clearer. So really, there's only how many forces here acting on this crate? 4, 5, or 3? How many real forces, how many actual forces are happening? It is actually not 4, it is not 5, it is 3. So that is it. Those 3 purple forces, Fn, T, and Fg, are the only forces acting. But when Fg acts, it really acts using its components, Fgy and Fgx. So that's the idea here. And that's why we went ahead and found those components, and that's why we did a redraw step. All right, let's go ahead then and and solve the problem. So I think in problem 5b, they're going to ask us either for the normal force or tension, and it looks like it's going to be normal force. And then in 5c, they're going to ask us for tension. Well, let's pretend we didn't read that, right, and didn't know that. So what I like to do is free body diagram, tilt the axis, do a redraw, and then just move to x and y direction. Now I'm talking about the new x and the new y direction. So which one do you want to work in first? And it doesn't matter, we just pick one. I think the problem asked us to solve for force normal first in part B. So that's the y direction, the new y. So I'm gonna go ahead and work in the y direction. But if you didn't read the problem and you're just like, oh, I'm gonna work, Mr. Rodriguez says pick a direction, x or y, work in it, then work in the other one. Let's give it a try. Let's just work off the y direction. So let's say we pick that. And in the y direction, we like to write Newton's second law. And with Newton's second law, we have to realize, is this a equilibrium situation where the acceleration is equal to 0, or non-equilibrium where the acceleration is some number? And that's really one of the big ideas with this chapter. So we have, let me say it again. So if the acceleration on this object is equal to 0 meters per second squared, we like to call this equilibrium. And if the acceleration is equal to a number, right? Maybe it's 1 meter per second squared, negative 1 meter per second squared, something like that, we call it non-equilibrium. Or we call it accelerated motion. One of those two. So that's pretty much what you have to decide with this problem. What are you dealing with here? And I'll tell you right now, because we're just kind of getting into this chapter, right? We're not close to the end yet. We're decently through it, but we're not close to the end yet. We're still, a little over halfway maybe. We are keeping it simple by only working with equilibrium situations. So you're seeing that in the friction lab, you're going to see that in the brick lab, and you're going to see that here. So that the equilibrium, that the acceleration is 0. So if we go back to this problem, in the y direction, what's the acceleration? If we look right here, there's two forces acting in the new y, right? And that is Fn and Fgy. They balance each other completely. We know that because the mass is not accelerating into the sky, and it's not accelerating through the plane. So they have to be equal and opposite. So that would mean that this acceleration right here is going to equal 0. All right, so what we can do with that is on the right side here, we can multiply our mass, which I think was 45. I had to go back and check. We can multiply that by 0 meters per second squared, which is just going to give us 0. All right. Now that's not always going to be true, right? Sometimes objects will accelerate down a hill, or they will be pulled up the hill and speed up. So acceleration can have a number, and it can point in different directions. What about the y direction? We said there's two y forces. So looking back at right here, right? The two y forces are Fn and Fgy. They both point in the new y direction. So we're only interested in the new y, right? That's all we care about. All right, so coming back down here, we can go ahead and call the upwards force the positive one, and that would be Fn. So we'll give it a positive sign. We won't give it any sign, which is implied that it's positive. We're going to sum it, right? Sigma, the Greek letter right here is sigma. This means sum or add, and we are going to add, or we're actually going to subtract, but we're going to add a negative number, which is the same as subtract. So we are going to go ahead and add negative Fg, or subtract Fg, right? So I have something like that. So down here, you can just carry this down. Fn minus Fg equals 0. And we learned, just like before, we can move our variables just like numbers. So we'll add Fg to both sides. We've been doing this in math class with x and y. Why can't we use Fg, Fn, and do the same thing? We can. So we can cancel the Fg's right here, and we see that Fn then is equal to FG. All right. Ooh, I see what I did wrong already. Not paying attention. Let me go back and fix it. So this was FGY here, not just FG. I have to be careful there, right? So let me go back and fix that. It'll be luckily an easy fix. So we can go ahead and add a Y here. Add a Y here, and here, and here, and here. So this just proves what we kind of knew, right? We knew that it was an accelerated motion, and we knew that the force normal would equal FGY. Now, I think in problems 1 through 4, we were getting easier problems where it was just equal to FG. And so this shows that our normal force isn't as strong as it used to be, right? By working with an inclined plane, it's actually going to be a smaller value. And the reason I know that is because if I go right up here to the original free body diagram and look at this orange triangle, you can see that FG is the hypotenuse, so it's going to be the largest side of that triangle, whereas FGY, which we just proved is equal to FN, is going to be smaller, right? It is the adjacent, so it's going to be smaller. So we want to use some SOHCAHTOA to solve for the adjacent of a triangle. So that's going to mean working with cosine. So let's go ahead then and keep working here, right? Let's find this adjacent, or FGY. So I'll start by writing here my cosine formula. And I'm going to use alpha here instead of theta. If I call it theta, no worries, and you know what I mean, it's alpha. So cosine of alpha is equal to the adjacent over the hypotenuse. So we can go ahead and plug in what we know. I think alpha was 35 degrees. I'm just going to go check because I don't want to make another mistake and then have it come back and be a problem. All right, so 35 is alpha. So I'm just going to write that, add that to my diagram, because like I said, I don't want to have that show up or forget. Okay, so all right, so the adjacent we said was FGY. And we also said that the hypotenuse was FG. So FG of Y then is equal to something. We're just going to have to solve it, right? We've done this before. So we'll multiply both sides here by FG. All right, and now we have an expression for FGY. All right, and we know that FG, or should know, is FG is equal to mg. So let's go ahead and add that in. And we want to know what FGY is, because if we know FGY, we know force normal. So let's go ahead then and keep going here. Oops. All right. I think we said the mass was 45. Baby G is 9.81. All right. And let's go ahead and plug that in our calculator. And take me a second here. Making sure we're in degrees and not radians. I am in radians. Right as I said that, I get a negative 398, and that means I'm in radians. So give me 1 second. And that was because of AP physics. We were working with sinusoidal waves, and that it has to be in radians. So we want degrees. All right, so instead of negative 398, I'm getting positive 361.61, which is the correct answer. So let's go ahead and write that down. And what are the units here? It is a force, so you should be saying at home newtons. Y is starting to look like an X there. All right, and And what we've done by solving for this 361.61 newtons is we've also found force normal, which is what we wanted, because we proved with Newton's second law in the y direction that force normal is the same as FGY. So we now know that force normal is 361.61 newtons. And so once again, force normal was smaller than FG. We never solved for FG, did we? What is FG? Well, it's 9.81 times 45, so about a little under 450. FG is 441.45. So it is indeed smaller. Why is this? Can we make sense of this? Well, let me show you. So we're saying, and I can probably write this, let's see. I think I said 361.61. Okay. All right. So what we're saying here is that the normal force, which is also 361.61, whoops. I don't know how I undo that. Okay. So what I'm saying is that when this plane is inclined, right, FG is still 441.45, but the normal force is smaller because the plane doesn't push back as hard on the mass, right? The gravitational force is now directed straight down, and the normal force only does as much force as it has to do, right? And FG of y, which pushes downward in the new y, is 361.61, so the plane only pushes back up with 361.61. It doesn't push down at 441.45 like it would if the mass or the plane was just sitting here like this, right? If it was just sitting here like this, like I'm drawing, then FG and FN would be equal and opposite, and they would both equal 441.45. So what you're seeing is that by tilting this incline, by inclining the plane, right, that the FG and FN gets smaller because it doesn't have to be as large now. It doesn't have to push back as hard normal or perpendicular anymore, because the force gravity is not pushing that way. It's pushing straight down. It's not pushing in the new y direction. So that is why. Okay, so hopefully that makes sense. I know that's a little difficult to understand, but I think if you understand that, then you're kind of you're better off than just looking at the equations, because the equations, while we might like doing math, they don't really show understanding all the time. So I find sometimes students can do the equations, but they don't really know what they're doing, or like, I don't know, I just do it this way because Mr. Rodriguez said so, and I know this is what you're supposed to do. So we're trying to understand or have a better logic than my teacher told me to do it this way, right? It's not good reasoning. Yeah, it's just not. Okay, so x direction. So I know the problem asks us to find tension x, but by working in the x direction, we are going to get that answer. So we don't need to go back up and read the problem. Let's just go ahead and start working. So we'll say the sum of the forces in the x direction is equal to max. And once again, this is the new x direction. So we have to go back up and look at our problem. So the new x direction, we can see that one of these forces, T or FGX, is going to be positive. And if we check what we said at the start of the problem, we said up the incline is positive x. We could have said down the incline is positive x. It's not special. It doesn't have to be up the incline, but it's what we decided. So T will be positive and FGX will be negative. Okay. So we're saying T will be positive, FGX will be negative. Add those two together. The mass of the crate or whatever this is being pulled is 45 kilograms. And now they told us that the object is being pulled at a constant velocity. So because they told us that, that means that this is equal to 0, right? That we are not accelerating, we're not speeding up or slowing down at all as the object is being pulled up the incline. And this constant velocity means the acceleration is 0, and therefore we have a 0 right here. And 0 times 45 is just equal to 0. All right, and just like last time, we want to solve for something here, right? So we'll go ahead and add FGX to both sides. And this allows us to see that the tension, oops, I forgot to cancel. Tension is equal to FGX. And so if we can just find FGX using some SOHCAHTOA, we'll know the tension. And this is pretty similar to what we just did before, except FG of X is going to be an opposite. So let's go back up and check that, but it's going to be the case. So here we see FG of X, right, hanging out here, but this isn't really going to help us right now. What is looking at this orange triangle. So we can see that FG of X is opposite alpha, right, in this orange triangle. So therefore, we can use sine alpha equals op over hip to solve for FG of X. Let's go ahead and write that down. Whoops. I don't know what this is doing. It's like trying to help me make a circle or something. I'm just trying to write sine alpha is equal to op over hip. All right, we said alpha is 35 degrees. The opposite is FGX. It's weird having, the X part be opposite, but that's the way it is based on whatever angle we get. The hip is FG. We know FG is mg, so could you have wrote mg right there? Yes, you could have. So whatever, we'll work with what we have instead. Multiply both sides by FG. Sends it over here, right? And the reason I knew multiply is because I had a fraction over on the right. So see some division, I like to do the opposite to move it, which is multiply. So now I'm going to go ahead and rewrite. And once again, FG is mg. You might say, well, we already knew it was 441 or something. We used our calculator to find that. Yeah, you're right. So I could just write it in, but I already forgot what it was. I know I wrote it a few times, but I think it was 441. But I'm going to go ahead and resolve just to be sure. So I have 45 kilograms times 9.81 times sine 35 is equal to FGX. Let's go ahead and get the calculator out. Now, I can already predict that this is going to be, based on this sine right here, 35, that this is going to be, of course, smaller than FG, right? Because it's a component, it's a part of FG. So smaller than a hypotenuse. But I can also say that it's going to be smaller than FGY because sine doesn't do as well with 35 with smaller angles. Sine likes the larger angles between 1 and 90. So sine likes things over 45. It likes working with angles 45 to 90 degrees. So I know this is going to be the smallest side of this triangle. So let's go ahead and multiply this. Yeah, it looks like FG was 441.45. So we'll multiply that by the sine of 35. Which is going to give us 253. Whoops. 253.21 units are newtons again. And so just like predicted, this is the smallest side of that orange triangle, 253.21 newtons. And I can add that in. Sometimes I like to do that just to... All right, it's right there. Okay, so 253.21. All right, so we want to know what tension is. And since we learned a second ago in the first part that tension is equal to FGX, we can say exactly that, right? That tension is equal to 253.21 newtons, right? Because all we're doing is we're taking this value and subbing it in right there, right? And so therefore tension is the same as 253.21 newtons. Good. So let's go ahead and add that up here. And you could say, well, what about the redraw? Why didn't you use the redraw? You can, right? I could have wrote those down here instead, right? I could have wrote the 253.21. I'm just writing them there for just so you can see what's going on. This wasn't a required step, but it's just helping us learn. And notice there's no units there, so if you want to write units on all those, it'd be newtons on each one. All right, and you see that the up parts are equal, the new y and the new x parts are equal. And that makes sense because this is an equilibrium situation. Yeah, the crate's moving, but it's moving at a constant velocity, so it's not accelerating. And forces are all about accelerations. All right, so that's it. We have it. We solved the problem. We started by drawing a free body diagram. 3 purple forces, Fn, T, and Fg. We then worked in the y direction to see that Fn is Fgy. We used SOHCAHTOA to find that Fgy is equal to 361.61 newtons, which is the same as Fm, which is 361.6 newtons. That's our answer to part B right here. Then we worked in the x direction and summed our forces there using Newton's second law, and we found that tension is the same as Fg of x. And then we used SOHCAHTOA to find that Fg of x is equal to 253.21 newtons, which is also equal to tension, and that solves our answer for part C. So that's it for question 5. Hopefully that makes sense, and you can check your answers at the back of the worksheet, but I'm pretty sure we got it. I can just go up here and show you. I think I have the back of the worksheet somewhere. Let's see, question 5, 5B 361, 5C 253. All right, that's it. Take care.